Well, I'd like to do actually a quick kind of where are we in mechanics at this stage in the year, because we're going to start a new unit on rotation, and this for the first time this year is going to be something kind of brand new from what you did last year. And I think it's a good time to sort of stop and summarize what we've done over the course of the year. First of all, we have been studying mechanics, as you know. And what is mechanics? Well, mechanics means that you're looking at the universe and you're saying two things. One, there's stuff out there. So we have objects, like 2 kilogram masses in llamas. And, and these objects have a lot of different characteristics. Like a llama has a certain texture of llama fur and a certain color and a certain mass and height and all that stuff. But we've identified one of those properties, mass, as being really, really important for some reason. So we talk about the mass of things a lot more than we talk about what color they are. And the other thing that we've done is we've noticed that these objects, so here's one, here's a green sphere thing or circle or whatever, we've noticed that they move. And there, it's moving. And we decided that it would be very interesting to observe that motion and describe it, and also ask questions about why and how things move the way they do. That's really been what mechanics is all about, is studying that things have mass and they move around. Okay, so how have we organized that study? Well, the first thing we studied, well, in a sense, we studied 4 different topics so far in mechanics. We studied kinematics, was the first unit, if you will. Then we studied dynamics, forces and stuff. And then we studied energy. And then we studied momentum. Okay, let's just say a couple things about each of these. But it's useful to sort of consider these as the big 4 ideas in mechanics thus far. But they differ in terms of their nature. For instance, kinematics, one could argue, wasn't really doing any science yet because we didn't ever ask why things happen. Just kinematics is purely descriptive. And we looked at these moving things. We looked at the screen ball moving around. And we decided that to describe how it moves, that we would first of all describe space. And we would describe 3 dimensions of space and 1 dimension of time. And from that way of describing space and time, we came up with quantities like position and displacement. Then we combined that with time, so we describe space as having these x, y, and z dimensions, and then we have time that we throw in with that. And then we combined these and invented all kinds of new quantities, and by all kinds I mean 2. We invented velocity and we invented acceleration. And then we considered for one very special kind of motion, which is amazingly rare considering how much we spend time analyzing it, for one special kind of motion, and that is uniform acceleration, which I'm going to pretend that ball just did, speeding up and then slowing down, that there are some relationships between velocity, time, and acceleration. We wrote the big ugly formulas and did all kinds of calculations. But keep in mind that kinematics, position, time, which I've listed here, velocity, and acceleration, and the relationships between them, is, as I say, purely descriptive. We learn how to say how things move, and boy, that ball accelerates or it doesn't. But we never asked why they do. We never said, why is that ball accelerating at 9.8 meters per second squared? We just said that it is, and that's good enough for us. Okay, that was kinematics. Dynamics is where we visited with Isaac Newton, who came up with the first law of motion. In other words, Newton said, why do things move the way they do? And we introduced the new quantity of forces, these interactions. We learned that the natural state of the motion of an object is to be either at rest or moving at a constant velocity. And what gets our attention is when things accelerate, because that requires an interaction with some other object. So a llama won't accelerate on its own. It has to interact with a huge rubber band, or it has to interact with the ground. It has to interact with another thing. And we call that interaction a force, and these forces cause things to accelerate. And so in the topic of dynamics, we learned how to say net F equals ma, and did tons of problems finding the acceleration of things when various forces act on them. I'm actually going to skip to the end of the list of momentum. These last 2, energy and momentum, physicists love these because they are quantities that are conserved. And as I said, I'm going to, and conservation laws are cool. They allow us to make grand statements that if you have a closed system, its momentum stays constant, and its energy stays constant, and that is cool, and it allows us to do fun problems. So I said I was going to skip to the last one, and the reason for that is that we saw, you may recall, that the conservation of linear momentum, I'm going to make the distinction here, linear momentum, defined P equals mv, vector, that actually follows from Newton's second law. So, Newton's second law, net F equals ma. If you know this is true, and we know this is true because we keep testing it over and over and over, and it keeps on working, that implies that, not P equals mv, I'm sorry, that's a defined quantity, that implies that momentum is conserved. So I'm going to move that arrow up here. All right. So those two things are related, but it still is useful to think of them as two really great ideas. The idea of how forces affect things' motion and the conservation of linear momentum. Energy is different, meaning this is a whole different law. And in fact, conservation of energy dates back to Newton in the 17th century. And conservation of energy is an idea that didn't really get formalized until 200 years later. Conservation of energy, because energy hides in so many different forms. Linear momentum doesn't. There's only one kind of linear momentum, but there's all different kinds of energy. So it took quite a bit longer to actually understand that energy is conserved and what a powerful idea that is. So there are the big four. Kinematics describes that things move, how they move. Dynamics and conservation of linear momentum are equivalent ways, if you will, of analyzing moving systems. And then conservation of energy is the last big idea that we can use to analyze systems and understand them and predict how things turn out and cool stuff like that. That's all I have to say about that.